So I'm really excited that our first keynote, Michel Bruneau, is going to get us started here. He's one of the really early pioneers and great thinkers, particularly from the engineering perspective, about resilience and in the design of structures and buildings, primarily animated by tremendous work he's done around the risk of earthquakes. But he's had a lot of wisdom over the years in acquiring that. And so, Michel, if I can have you come up here now and share your keynote, and then we're going to shift to a panel discussion. I'll introduce the panelists shortly. Thank you.
Thank you very much. It's a pleasure to be here. I'm not sure I can deliver on wisdom, though. That's not my specialty. But we'll talk about challenges on the road to engineering resilience in some of the ways that might be of interest here. And let's get started on that. Interestingly, the first time I ever heard the word resilience was in 2001, when we were sort of in a room, a dozen of us, trying to think what's the most important thing that should be done in earthquake engineering in the future. And we sort of came up with this idea of achieving earthquake resilience of communities. And you've seen these curves ever since. And since then, I mean, resilience seems to be everywhere. San Francisco has a resilience plan. New York City has one. Tokyo has one. There's been initiative for low carbon and resilient cities, a stronger resilient New York. The Rockefeller 100 Resilient Cities that you've heard about, I'm sure. The Earthquake Engineering Research Institute had a distinguished lecture on resilience. The 16th World Conference in Earthquake Engineering had a byline that you can see at the bottom here that says, resilience, the new challenge in earthquake engineering, which could be interpreted in two different ways, actually. And so it's just a matter of time before somebody names a city resilience in somewhere in the US. So in 2010, I did a bit of a very scientific study. I Googled the word resilience and came up with 8 million hits. And so let's go a little bit further. Google Obama plus resilience, got 500,000 hits, which can be explained because Obama had set a mandate to all the federal agencies to tackle resilience. Engineering resilience was not as popular a term on Google. And quantifying resilience, by far less popular. And then quantification of engineering resilience got one result. That's something very difficult to do in Google. It's called a Google whack. I repeated the experience a little bit later, but before we go there, what I sort of got from this is that everybody seems to be talking about resilience, and they don't necessarily understand each other then, maybe. If I did that in 2016, what I noticed is that every item got an increase by a factor or 2 or 3, except the word resilience itself that increased by a factor of 6. So resilience is becoming the new buzzword, and if everything is resilience, then nothing is resilience. It gets difficult to talk about it. So I'll sometimes look around on the websites and see what else can I find, and this is the U.S. Department of State in the United States that talks about resilience. And I'm not going to read all of this, but at the bottom they have a little bit of a list of what should you do to become resilient, and there's another long list which I'm not going to read, but one of the items at the bottom says, if you want to be resilient, laugh. That helps you to be resilient. So rent a movie that makes you laugh and all of these good things. And I'm sure it has some connection to resilience. But if we go back to the definition of resilience from the dictionary, and you can pick any one of the dictionaries you enjoy. They're all a little bit different, but they talk about something that returns to its original shape after it's been pulled, stressed, bent, whatever. And some dictionary says return to original form or spring back into shape. And then the ability to recover readily from a bunch of things that can be illnesses or misfortune, or recover quickly, or be strong again, and what have you. So the bottom line, it's the quality of being able to return quickly, and so the quickly is an important thing, to a previously good condition after problems. So the three things is return, previous condition, problems. So therefore, if we think of that, resilience must address some sort of functionality, and it can be many things. There's different functionalities depending on whether you're talking about physical infrastructure or organization or services and what have you. And it must address the loss of the functionality and the recovery of that functionality in time and in space. So, for example, it could be, the functionality could be a residual strength over a needed strength. It could be an available space over an original space. It could be number of customers served over the total number of customers, waiting time in emergency conditions versus normal time. And of course, some of these definitions apply or do not apply depending on what you're looking at. And there could be other definitions depending on the context. But it's all about a functionality of some sort. And then it's not clear how we define the functionality. We had a research project looking at hospitals, and we say, okay, we're losing function, we're recovering function, but what is it exactly that is the function of interest here? And there's many options, even for something as simple as a hospital. I'll give you some examples. One of the items we had considered originally on was quality of life in terms of having a healthy population. So you base correct for population growth over time, and you call that 100% healthy population. An earthquake happened, you have loss. If there are going to be some deaths, you're never going to recover to the fully healthy population. But if there's no death resulting from loss of hospitals, maybe you can recover to that point. If some hospitals collapse or you lose some healthcare capacity, then you can maybe not recover fully. And of course, it's kind of, there's a number of people who won't be dead, but they'll have long lingering debilitating conditions, and so that's not healthy either, and that's not going back to the baseline. Now the problem with that is it's great, it's a true global impact on the population health, but it's really hard to define what is healthy or unhealthy and what's the causality of the death to the earthquake. Maybe some people would have died anyhow without an earthquake. It cannot be related to engineering quantification easily. If you're really rich, you can get treated somewhere else outside of the earthquake zone. You can get flown to New York, and if you're in California. So it's a tremendous problem. It's huge. It's important. But it requires massive research funding that's probably not there to tackle that problem, and resources. So we sort of got a little bit more humble, and we looked at patients per day as the capability of the healthcare system in a region to treat patients. And in California, for example, there was a bill to make hospitals earthquake resistant, and so that led to many hospitals being shut down. So there's a bit before the earthquake of a loss in the treatment capability in California that happened. But you could argue that maybe these are people who would have died in collapsing hospitals at the time of the earthquake, so it's sort of an uneven trade-off. And then there's an earthquake that happened, and then you have to repair the facilities, and you have to rebuild the capability. And it also highlights that at the time of the earthquake, there's some parking lot MASH-type operations that can happen in treating patients in the parking lot, which you can do in California, but obviously cannot do in New York City in the middle of January. So it's very much a temporary measure, and you shouldn't let that distract you. The advantage, of course, is that it's focusing on the facilities themselves to provide services, so an engineering approach is possible, but not easy. It's still complex because there's lots of structural and non-structural components in hospitals, and there's a lot of modeling challenges that have to be done there. But you can develop a methodology and a framework, nonetheless, that can support decision-making systems, and that can be used as a way to show the benefits of reducing probability of failures. So let's keep that in the back of your mind. Let's jump now to the Christchurch earthquake that took place in 2011. In fact, it's a series of earthquakes, as you can see from all the dots there. But the one of interest is this magnitude 6.3 that happened 5 miles from the central business district, which is the little yellow box that you see here. So we'll do a little bit of an experiment. This is a central business district. Pick a building somewhere in that central business district. Keep your eyes on it. And this is 2 weeks before the earthquake, and this is 3 days after the earthquake. And if I go back and forth, chances are there's probably the building you picked is still there. The light has changed. The angle of the photograph is not the same. The cloud coverage is a little bit different, but I suspect you probably still have your building there, unless you're from New Zealand and you knew where to look to pick the 2 buildings that collapsed. And that's the only 2 buildings that collapsed. And even if you were from New Zealand and you picked, say, the Forsyth Bar building here that did not collapse but lost its staircases for 15 stories, so people had to be creative in finding ways to evacuate the building, or this Grand Chancellor Hotel, which was leaning precariously due to structural damage, from an aerial view you would not be able to tell the difference. Now let's do another experiment. Instead of looking at one building, take a global look at the central business district here as a whole. This is 3 days after the earthquake. This is 14 months after the earthquake. And if I go back and forth, there's a noticeable difference between the two. In fact, Christchurch was turning into a parking lot because thousands of buildings were being demolished, not because of earthquake keeping them more and more and more damaged due to the aftershocks. No, not at all. They were buildings that were damaged by the main shock, demolished by human activity to replace them by new buildings after the earthquake. And so there's something there that I will come back to. But if we look at the Christchurch Business District in terms of resilience, what happened after the earthquake is this, everybody was evacuated from the central business district. It was fenced off by National Guards preventing entry essentially for many weeks, and then eventually it was literally fenced off so that nobody could get in there. And so then that created a number of frustration. If you were the owner of a building that did perfectly fine in the central business district, you still could not get to it. If you were the owner of a restaurant, you could not retrieve the food or the money in the cash register. I visited a hotel where I remember vividly in the room, you could see on the desk next to the bed, the purse, the wallet, and the passport of whoever was in that room, and that was 5 days after the earthquake, and they were not allowed to retrieve that information. So 2 years after the earthquake, a third of the city was still fenced off. So as far as resilience, it was a very slow process, even to give back access to the city, not, mind you, reconstructing the city. The reconstruction process is underway, but if you keep parts of the city fenced off for 2 years, there's another type of damage that grows up on you eventually, makes things a little bit more challenging. So I'll come back to Christchurch in a moment. What I'd like to do in this presentation is bring 3 structural engineering dilemmas that we have to deal with as structural engineers that sometimes you don't have to deal with in other aspects of resilience, but I think that matter. The number one, and this is probably one you also have to deal with in any other aspect of resilience, is that resilience of the engineered infrastructure is something many don't care about until after the disaster. And we're always concerned before the disaster. So that brings a question, for example, why the hell do we design for earthquakes if we know that this very famous story that I suspect you're familiar with, the 3 Little Pigs, is pretty much what we live in. All my friend engineers believe that this is the way to go. You do something that will be good and will prevent against the big bad wolf. But our human nature is on the left of the picture. And that's where we want to be. It's more carefree, enjoy life, and don't spend all that money. Because after all, if the big bad wolf does not come, they probably made a better decision on the left, right? They used their money for something else. So that's the challenge we face, and it's a bit of a tricky thing. And it manifests itself in other hazards as well. I happen to have many people I know in the northeastern part of Florida, and they were always telling me, there's no hurricanes in northeastern Florida. And they had all the fanciest explanations to explain that. They were non-scientific. They were sort of urban legends, you know, how the shape of the bottom of the ocean is such that there's no hurricanes here and things like that, which go figure. But of course, I never believed it. But the Hurricane Matthew sort of changed that urban legend into reality. And Hurricane Matthew was a Category 4 on track to hit and hug the coastline of Florida from south to north with the wall of the eye of the hurricane following the coast. That was the prediction. And if that would have happened, 10 million people would have been affected and would have had a direct hit from the wind. Fortunately for them, it stayed 25 miles offshore, so they did not get the massive super winds that were expected. But a hurricane is a counterclockwise movement, and so the wind was pushing the water towards the shore as the hurricane was moving up north. And as a result, if you were at low tide, you got high tide because of the storm surge of the water coming towards the shore. So whoever was the lucky person at high tide to get the hurricane next to them was the one who was going to get the storm surge. So it's like a double high tide. And so Flagler Beach is pretty much where it happened. The beach disappeared, the dunes disappeared, part of A1A, the road along the ocean, disappeared, and they're still nowadays trying to rebuild the road 3 years after the event. And you tell people, well, why did you get this strange belief that there's no hurricanes in Florida? Because these are sort of the path of all of the hurricanes in the past 100 years across Florida that were massive, massive hurricanes. And I don't see anywhere there where you can feel pretty safe, and certainly not northeastern Florida is not outside of that path. So there's an approach that you can say, fine, we'll deal with it. And some you may deal with it with insurance, you may deal with it with other ways. And I think it's okay if you do it conscientiously and you say, we'll deal with it, and I'm aware we might lose everything and we'll rebuild. As long as you're aware of it and you accept that. But where it gets tricky is that people sometimes don't know it, and it leads to strange circumstances. For example, if we do a car analogy, the way cars are designed is if you run them on a wall, there's a crash zone at the front that absorbs the energy, and that is essentially done such that the car itself is a write-off, but the occupants are safe. And this is good, but sometimes people think that they buy this on the right. They don't. That's much more expensive. But that analogy is rare. People don't buy a car thinking they're getting a tank, but they buy a building thinking they're getting a tank. And buildings are designed the exact same way as the cars are on the left. And this is an analogy that has served earthquake engineering for decades, where we're going to build buildings that don't collapse so that the occupants are safe. And with the exception of the 2 buildings that collapsed in Christchurch that are a very old vintage of construction, most of the buildings in Christchurch did fine. They did not collapse and the occupants were safe. The problem is the analogy breaks down a little bit because it's not one car crash. It's like everybody's in a car crash at the same time. And that's what happened in Christchurch. Everybody was in the car crash at the same time, and they had to deal with it, and hence the situation that we've seen. There's an interesting report if you're on the engineering side and you're interested to see what's happening as part of the reconstruction of Christchurch that you can download for free from the website that is shown here. We encourage you to send and share the link with your friends as opposed to sending them the PDF, because we have a counter. We're trying to count how many times it's been downloaded. So if one person downloads it and send it to everybody in China, that's one download instead of a million. So we prefer to count. So far we're at 6,000, and hopefully we'll continue getting interest in that report. But it focuses on the reconstruction process itself. So how have the structural engineers changed their practice based on the damage that occurred in Christchurch? And it has been a tremendous amount of changes for that matter. And a lot of the changes have happened because the engineers said, oh, the buildings behaved exactly as we expected them to, so it's a success story. And of course, for the people at Christchurch, they don't necessarily see that as a success story. They say, oh, that's exactly what they were supposed to do. Maybe we can do better than that. And so there's a whole section of the report where we're discussing, based on interviews we've done with all of the structural engineers involved in the reconstruction process, we've sort of listed the hierarchy of priorities among various segments of the population, tenants, developers, architects, and engineers, to see how the earthquake has affected practice and specifically the choice of structural system, and see if some of those are more resilient or not. Although the focus of the report is on the reconstruction, not on resilience. And what we find is that a lot more structures now are being built in steel. In fact, where Christchurch was probably 95, 98% reinforced concrete construction, now the new buildings that are being built are 80% steel for lateral load resisting system, 5% reinforced concrete, all of it in reinforced concrete, and 15% reinforced concrete walls with steel gravity load systems. So steel is taking over Christchurch. It's like the new city. And there's a tremendous amount of different types of structural system, which is a presentation by itself. But what we've seen is that the trends as to what was the driver in deciding on the type of structural system, if we did the bar chart by number of years and what led these choices, request by the tenants, which used to be an enormous driver following the earthquake, is receding back now in time. The structural engineers proposing a solution and getting it accepted is a constant, and cost as a driver of the decision is going back now with a vengeance as being a driver. And so as people sort of forget the earthquake or getting further from the problem, they're sort of changing their decision and how it drives structural system. So in structural engineering dilemma number 2, how can a structural engineer contribute to quantifying resilience? There's a number of ways it can be done. One of it is to help define the weight to give to the physical infrastructure as part of the global resilience framework, because that sometimes is forgotten. So for example, there's many frameworks out there. This is the People's Frameworks that spells out the various dimensions of resilience if we want to achieve a resilient community. The engineered infrastructure is the second P in here, in the physical infrastructure. And so when we add up all of these resilience calculations together to aggregate them, it's important to realize that the physical infrastructure is more than 1/7 of the problem. So we need quantification methods. How do we quantify resilience? There's many ways to do it. There seems to be no consensus on which method, but I think if people are to work together, they have to sort of agree on a method to work together with. You've seen this resilience triangle before. Of course, the idea is to make the triangle as small as possible over time. Maybe someday we'll get rid of it altogether, but we're not there yet. And so there's various methods to quantify these things. The areas under this curve is one way to quantify resilience. It's one that's interesting because it's a continuum. It gives a value for itself. So if the value is 1, you're fully resilient. If it's 0, you've lost everything. And then the area gives you a weighing factor of how much in between you are. You can do mathematics with the loss function. How fast is the loss? And in an earthquake case, it tends to be pretty abrupt. The recovery function, how fast are people returning to the situation when they can go to better than before, which I think is what Christchurch is probably going to end up with. Or you could do it, you'll never be as good as before, depending on where you are and what kind of resources you have. So the key being functionality. The low-hanging fruit has been the metered distribution systems, because it's easy to get the data on those things compared to maybe buildings. And so a lot of the studies on resilience, it seems, have focused on that, such electricity distribution or water distribution. And that's all good, and that's all very useful. And so, for example, these are rapidity curves, actual from data following earthquakes in California. That's pretty old now, it's at least 10 years old, but still, from after some earthquakes, how fast has the service been returned to the public? And there's so many of those curves in California that you can do some statistics on them and establish annual probability of resilience of having so many people having power in so many days following an earthquake. And so that's good. But it's an interesting thing now that once you start to calculate resilience using something like that, this is after the Tohoku 2011 earthquake in Japan. We did the resilience calculation in that case for power, gas, water, and what have you. And you find that in the Fukushima district and the Miyagi district and the other one next to it, the resilience is pretty low. And in the other districts far away, the resilience is pretty high. And that leads to an inconsistency right there, because everybody is pretty much the same power and water distribution system. So really all it means is that they were closer to the earthquake than the other districts. And so there's got to be a way to calibrate resilience as a relationship to demand as well. It's not just how you measure up, but it's how badly stressed you were as well. So these measures of resilience can be improved. Another way to improve them maybe, and that's where there's some interest maybe to better understand human behavior. If you have 100% loss of power for 2 days, so that's 100 times 2, that's 200 for the area of that little box there, is it the same as having 10% loss of power? Loss of power for 10% of the population for 20 days. And which box would you prefer to be in? It depends on pretty much on what's your business model and a number of things like that. And change those from 2 days to 20 days here, and 20 days here to 200 days here, and you get again a different set of answers depending on what business you're in. So that's the nonlinearity of that area really, and nobody's ever looked at that as far as I can tell. And there's a third thing that is a bit tricky with these low-hanging fruits of power and water, is that some measures can be faulty, because if you use the data from the utilities, it turns out that sometimes people have power without the utilities. So in Buffalo a few years ago, there was a winter storm that shut down power in 2/3 of the city for a week or so. People were pretty upset, and in some neighborhoods where they could afford it, everybody bought a generator. So now if there's a loss of power in my neighborhood, I hear all the generators starting up, and nobody has a problem because everybody has power from their own backup generators. But if you use the data from the utility, it says, oh, nobody has power, bad. But everybody's resilient now because they have bypassed essentially the power grid. So But still, this is good stuff. Now, engineering, structural engineering, quantification can be a little bit tricky for an individual building. There's no time to go through that today. We've tried it in 2007 using a three-dimensional bell curve and running that bell curve over a multi-dimensional response for engineering resilience operations. So that was the acronym SOMBRERO, using an orthogonal limit space environment, which is the OLE. And so it ended up working with the fragility curves, connecting them to resilience curves, and that worked okay, but I think it's a much more difficult thing sometimes to do. But nonetheless, we come back to this resilience curve at the top, and the path here to how far it drops depends on robustness. The more robust, the less it drops. And so if we overlay a curve for losses on top of that, you have the initial losses, and then the losses that take place during the recovery time. And when we do resilience and we focus only on response and recovery, we're trying to push this curve down here and to reduce the losses that take place after the event. But sometimes people forget the mitigation part at the beginning here, which is if you don't mitigate anything, you're just going to get those losses no matter what. So you can be super efficient and super good at being rapid after the event, but it sounds like there are efficiencies at being really good at mitigating the losses at the beginning as well. And this is one important role that the engineers can take on, which is creating resilient infrastructure to minimize not only the time to recovery, but the loss of functionality at the beginning itself. So there's some examples of how this could be done using structural fuses without going in great detail. Maybe today it's hard to relate to fuses because everybody has breakers in their box, but it's a fuse, it's a replaceable piece in an electrical component system where it takes the impact and then the whole house doesn't burn down, and it's easy to replace. And the easy to replace is the key thing there. So here's an example in a bridge application where we're using buckling restraint braces to dissipate the energy of the span moving around instead of putting damage in the columns of the bridge, which is the common way of doing it nowadays in an earthquake region, which doesn't seem to make sense because we would be putting damage in the gravity carrying system when we do that, but that's how it's done. So here's an example of buckling restraint braces being tested on the shake table. And it's not very dramatic because all the yielding is done inside that yellow box here, so you don't really have much to see other than the structure is shaking. It's in good shape after the earthquake, and we wanted to show that it can be replaceable. So we asked our technicians to take each of these yellow things out of the frame and put a new one. So you can see the first floor being replaced here, and they'll do the same thing for each of the other floors. And the reason they're taking the floors out is not something you'd have to do in a building, but this is a third scale model, and I've not found third scale technicians yet, so we're sort of trying to deal with that. But it also shows how fast our technicians work. But so here's an example application of the buckling restraint brace into a bridge so that it would prevent damage to the column. So there's other things that are coming into practice built on this idea of fuse. This is an easily replaceable element that you would replace after an earthquake. The rest of the structure would be elastic and undamaged. Another example of that is a rocking frame here. These frames that you see that are massive are essentially free to rock from their base. And in between them, there's some energy dissipator elements that, again, would be very easy to replace. And they're not part of the gravity resisting system, so it would not affect, their damage would not affect anything as far as the gravity carrying capacity of the structure, which is a good thing. So we also need multidisciplinary collaboration to address a problem of resilience as we scale up to a community as opposed to individual structures. And so if we look at this multi-dimensional space here, we have on the vertical axis the people's framework where all these multidisciplinary collaborations would take place. We have a geographic scale from one structure to a whole country or anything in between. And of course, there's different performance levels that are expected for the infrastructure. And so one way one can think of resilience is if we talk the same language or quantification format, we can integrate essentially the resilience that would be calculated on all of these dimensions for a given geographic region. And then the key there, of course, is that by adding them together, they have to be weighted together. And I've been an advocate that the physical infrastructure should be weighted maybe a little bit heavier than the other component, not because the other components are not important, but because I'm more from the earthquake engineering field, and if there's no damage to the infrastructure, a lot of the other problems resolve themselves automatically. So There's also integrating over the area of the geographical area of interest. And that's a little bit tricky because some effects span greater than the area of interest. Like we think of the grid, the power can come from pretty far, right? So but nonetheless, that's some of the ideas that were thrown in there. The third structural engineering dilemma is that making a disaster-resilient community requires multiple owners and stakeholders which have various priorities, values, and interests to similarly embrace resilience. And that's not an easy thing. For networks, power, water, it seems to be easier again. Sometimes there's a single owner, sometimes there's a consortium of a few independent owners, and sometimes it's thousands of owners that are together, but they're together in the same game. For example, in the case of a single owner, a Department of Transportation pretty much owns all the highways in the state in which they have jurisdiction, and they can determine what will be their lifeline routes following an earthquake, and they can put money to make sure that bridges and infrastructure along those routes are going to be operational following a major earthquake. So they're capable of making these omnipotent decisions that is not so easy to do with buildings. For example, this blue building in this picture did extremely well during the earthquake in California there. The only problem is that the neighbor did not do so well and shed its masonry wall on top of its roof. And all the damage you see here is due by the falling bricks from the neighboring building. So you could have the most resilient building and a sloppy neighbor, and that amounts to nothing in the end. So if we're going to do a lifeline building, it really does not exist by itself if it's not surrounded by lifeline buildings or if it's not on a self-sufficient lifeline island. So on that basis, coming with resilient communities might be decades away from some hazards, and that's a challenge by itself. So it raises an interesting question. Can a community be resilient if all the lifelines, such as bridges along major evacuation and supply routes, and hospitals, are designed by strict state-enforced guidelines and made resilient, while all the other buildings are not? And let's take a look at Christchurch. In Christchurch, the hospitals were fully functional. One overpass bridge was damaged, and it was easy to bypass that bridge because it was not over a river, it was over other roads. All the roads were open once cleared of the debris. And somebody said Christchurch was very resilient. Only 2 buildings collapsed. And I says, what? I mean, we're halfway through a 15-year reconstruction of the central business district. 15-year may not be considered very resilient as far as rapidity of reconstruction is concerned. And that's, to me, it's a game changer because the work we've done at MCR for 10 years trying to accomplish resilient communities in the perspective of earthquakes, we focused on critical lifelines, bridges, hospitals, water, power, and we had all of that working in Christchurch, and the central business district is a mess. So that changes perspective a little bit, and it means we have to look at individual buildings as well, and it makes the problem a lot more complicated. So community efforts at enhancing resilience at times are counter to the best intentions of structural engineers because sometimes resilience is pursued without resilient buildings. There's something in the US called the US Resiliency Council that gives a rating, 1 star, 2 star, up to 5 stars to buildings depending on how they're resilient. It's a little bit based on the same thing as the green buildings and as a concept. There's some people criticizing it because they say, well, you can get 5 star and you may not be perfectly resilient and this and that. But I think it's good because it forces the owners to talk to the engineers and understand the choices that they have at their hand and how they can address the problem. So if just creating that conversation is huge. It has sort of happened naturally after the earthquake in Christchurch, but using something like this sort of forces the conversation prior to the fact. So, with all these structural engineering dilemma, we have that many owners do not want resilience or they don't even know why they should want it. A resilient building may be pointless unless the entire community is collectively resilient. Resilient buildings are good, but community resilience, of course, is more than resilient buildings. And achieving community resilience 1 building at a time may end up taking a long time. So what to do? Any crazy idea at this point is welcome to speed things up. And so I'm going to throw one in the mix, and I can easily see how it could be criticized, but at least we're throwing one up and others can follow. A near-term proposed concept, the Lifeline Resilient Building District. Figuratively speaking, it's not a real island, but it's an island of building that would all have 5-star USRC resilience rating. They would be connected to transportation lifelines to not be encapsulated and to link to critical facilities like hospitals if needed. They would have their own emergency backup power generation and water treatment and all these thugs, and probably also security forces for reasons that after the earthquake might become obvious. Now you may say that's maybe strange. Keep in mind that in the United States, there's a lot of gated communities going around nowadays that have their own sets of rules, and it's foreseeable that one could create a gated community from scratch that would be resilient. Why not? And so we call that the Resilient EPCOT, the Experimental Prototype Community of Tomorrow. You may have heard the word EPCOT before because there's an amusement park in Disney World that's called EPCOT. That's sort of a conversion of what the original Disney idea was, that it was supposed to be, EPCOT was supposed to be not an amusement park, but an experimental community of tomorrow, like the one shown here, which is from the drawings of Disney before his death. So that was the idea, so we would have a resilient EPCOT. So in conclusion, we need resilience frameworks, we need quantification methods, we need strategies to enhance resilience, and we need multidisciplinary collaboration. Once you pick a hazard, and we can have a call, focus on it, get all the functionalities needed, and integrate them across dimensions. Innovative and integrated solutions are key to enhance the resilience of infrastructure against extreme events. Of course, it'd be important to expand beyond single hazard solution to address multiple hazards without incremental cost. Multidisciplinary research requires a substantial investment, and that's where the research sometimes the dollars fall short. And then you want to consider one or many resilient EPCOT as part of your menu of solutions. And finally, most importantly, remember the State Department recommendation to laugh. And when we were in Christchurch following the earthquake, we were looking at damaged buildings, and we were tapped on the shoulder and turned around, and there was a clown. And this is very interesting. That was a clown doctors. They're all doctors going around and making sure that people who were part of the evaluation of damaged building would not get too depressed, I guess, or something like that. So that's somehow contributing to resilience. So I'm ending on this slide in case you want the link to download the Christchurch report, and I thank you for your time.
Thank you very much, Michel.